For 6 minutes and 52 seconds, the engineers in Pasadena could do absolutely nothing. The signal had already been sent. The rover was already falling, and no one on Earth would know if it had survived until it was already over. That gap, nearly 7 minutes of enforced silence between a command and its consequence, is not a technical footnote. It is the defining condition of every single thing humanity has ever attempted on Mars. And it tells you something about the planet that no photograph ever could. Mars is not simply far away. It is far away in a way that breaks the basic assumptions we bring to every other kind of exploration. When Apollo astronauts were on the Moon, mission controllers could speak to them in real time, with only a 1¼ second delay. The Moon felt close enough to manage. Mars, depending on where the two planets sit in their orbits, sits between 3 minutes and 22 minutes of light travel time from Earth. At its farthest, a round-trip signal exchange takes nearly 45 minutes. You cannot pilot anything there. You cannot troubleshoot in conversation. Every machine we have ever sent to Mars has had to think, at least a little, for itself. That constraint has shaped the entire history of Mars exploration in ways most people never consider. It is not just an engineering inconvenience. It is a philosophical forcing function. And as we stand at the edge of the most ambitious chapter of that history, it is worth going back to understand how we got here, and what we still do not know about the place we are trying to reach. The first time we got a real look at Mars up close, it ruined everything. In July of 1965, the Mariner 4 spacecraft flew past Mars and returned 22 photographs. Scientists, journalists, and the public had spent decades imagining Mars as a world of possibility. The astronomer Percival Lowell had mapped what he believed were vast canals, engineered waterways crossing a dying but inhabited world. Science fiction had populated Mars with ancient civilizations. The expectation of life, or at least the conditions for it, was not fringe speculation. It was culturally mainstream. Mariner 4 returned images of craters, hundreds of craters, a cold, thin atmosphere, apparently dead and battered surface that looked, frankly, more like the Moon than anything alive. The atmospheric pressure was measured at less than 1% of Earth's. The planet had no detectable magnetic field. The ultraviolet radiation reaching the surface was intense enough to sterilize most known life forms. In a matter of weeks, the romantic Mars of canals and civilizations collapsed entirely. What replaced it, for a generation, was a narrative of disappointment. But here is where the story turns in a direction that should feel deeply familiar by now. Disappointment in science is almost always temporary. It is a function of the instrument, not the truth. By 1971, Mariner 9 became the first spacecraft to orbit another planet. And as it settled into orbit, a global dust storm was raging across Mars, hiding the surface almost entirely. The team waited weeks for it to clear. When it did, they saw something no one had anticipated from the earlier flybys. Volcanic features so large they redefined the scale of what geology could produce. Olympus Mons, a shield volcano roughly the width of the state of Arizona, rising 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest above sea level. And more striking still, Valles Marineris, a canyon system stretching 4,000 kilometers, as long as the continental United States is wide, in places 7 kilometers deep. This was not the Moon. This was a geologically violent world, one that had once been capable of extraordinary things. And then the detail that changed everything again. Sinuous channels, dry riverbeds, features that could only have been carved by one thing, liquid water, moving in enormous volumes at some point in the Martian past. Mars had not always been what Mariner 4 photographed. It had been warmer, wetter, possibly, for a window of geological time, hospitable. The question that has driven every Mars mission since is essentially this: how long was that window, and was it long enough? The Viking landers arrived in 1976. They remain, to this day, the only spacecraft explicitly designed to search for life on the Martian surface. Each lander carried a biology package, 4 experiments designed to detect metabolic activity in Martian soil. And when the first results came back, they were baffling. One experiment, the labeled release experiment, produced a positive result. Martian soil, when exposed to a nutrient solution, released gas in a pattern that on Earth would indicate biological activity. The principal investigator, Gilbert Levin, believed until his death in 2021 that the experiment had detected life. The broader scientific consensus concluded the result was caused by reactive chemistry in the Martian soil, peroxides and perchlorates oxidizing the nutrient solution, not by microbes. The gas chromatograph mass spectrometer found no organic molecules at the parts per billion detection level, and without organics, the argument for biology collapsed for most researchers. But here is the thing about that conclusion that deserves to sit uncomfortably. The Viking biology results were not refuted. They were explained away by an alternative hypothesis that was also not proven. Science settled on the chemical explanation because it was simpler and because the alternative was extraordinary. That is a reasonable heuristic. It is not a closed case. In 2008, the Phoenix lander confirmed the presence of perchlorates in Martian soil, the reactive chemicals that the alternative hypothesis had predicted. That confirmation seemed to close the Viking question for good. Except that, in the same years, researchers studying Earth's Atacama Desert, one of the driest and most Mars-like places on Earth, found that microbial life survives there in part by metabolizing perchlorates. The chemical that explains away Viking is also, in some Earth environments, a food source. The certainty cuts both ways. This is the rhythm of Mars exploration. Every answer carries a new question inside it, coiled and waiting. The Curiosity rover landed in August of 2012 inside Gale Crater, a site chosen because the layered sedimentary rock at its center, Mount Sharp, represents billions of years of Martian history stacked in readable form. What Curiosity found in its first 2 years fundamentally shifted the scientific conversation. The crater had once held a lake. Not a brief, shallow pool, a long-lived lake system, potentially stable for hundreds of thousands to millions of years, with water chemistry that was, by the measurements available, broadly habitable for the kinds of life we know on Earth. Ancient Mars had not just been wet. In places, it had been persistently, stably, chemically welcoming. The Perseverance rover, which landed in Jezero Crater in February of 2021, pushed this further. Jezero is an ancient river delta, a place where a river once flowed into a crater lake and deposited sediment in exactly the kind of layered, fine-grained record where microbial biosignatures, if they exist, would be best preserved. Perseverance began doing something no rover had done before, caching rock cores for eventual return to Earth. Those samples sit in sealed titanium tubes on the Martian surface right now, waiting for a retrieval mission that has been planned, debated, redesigned, and not yet launched. If and when they arrive in Earth laboratories, they will face analytical tools orders of magnitude more sensitive than anything we have ever sent to Mars. The question of past life may ultimately be answered not by a discovery on Mars, but by a sample sitting on a laboratory bench in Houston or Paris or Tokyo. But the story of Mars exploration is not only about the past. It is increasingly about the future, and about the specific, concrete, deeply uncomfortable realities of putting humans there. The surface of Mars is hostile in ways that stack on top of each other, in ways no single sentence can fully capture, but try to hold them all at once. The atmospheric pressure is less than 1% of Earth's, meaning any exposed liquid water instantly boils away, and a human without a pressure suit would lose consciousness in seconds. The average surface temperature is around -60 degrees Celsius, though it swings by more than 100 degrees between day and night at some latitudes. The thin atmosphere provides almost no shielding from cosmic radiation. A Mars surface mission lasting 500 days would expose a crew to radiation doses approaching the career limits recommended for astronauts in low Earth orbit, and that is before accounting for solar particle events that can spike radiation levels dramatically and unpredictably. There is no global magnetic field to deflect those particles. There is no ozone layer to absorb ultraviolet. The soil contains perchlorates, which are toxic to humans and would contaminate any food grown in it without substantial processing. Dust storms, which can engulf the entire planet, would reduce solar power generation and clog every surface they touched for weeks at a time. None of this is an argument against going, but it is an argument for understanding what going actually means. The distance problem has not gone away. A human crew on Mars would face the same communication delay as every robotic mission before them. In a medical emergency, There's no calling Earth for guidance and hearing back in time to act. In a systems failure, the crew must diagnose and repair with what they have, because no resupply mission can reach them in less than months at minimum. The psychological literature on long-duration isolation is sobering. The human factors may ultimately be harder than the engineering ones. And yet, the MOXIE experiment aboard Perseverance, a technology demonstration roughly the size of a car battery, successfully produced oxygen from the Martian atmosphere by separating carbon dioxide into oxygen and carbon monoxide. It produced small amounts, enough to sustain a small dog for roughly 10 minutes in a single run, but it proved the principle at Mars, in the actual Martian atmosphere, under actual Martian conditions. A scaled-up version of that technology is one of the foundational requirements for human presence on Mars: breathable air and oxidizer for rocket propellant to come home. A device that fits in a car is now the proof of concept for the life support and return fuel of an eventual human crew. The helicopter Ingenuity, which arrived as a technology demonstration alongside Perseverance, was designed to fly 5 times. It flew 72 times before a rotor blade broke on its final flight in January of 2024. It flew in an atmosphere so thin that achieving lift required rotor blades spinning at nearly 2,500 revolutions per minute, about 5 times faster than a terrestrial helicopter of comparable size. It photographed the rover from the air, scouted terrain, and demonstrated that aerial reconnaissance on Mars was not just theoretically possible but operationally useful. When Ingenuity's successor vehicles fly, and they will carry science instruments. They will see geology that no ground-based rover could reach. This is how Mars exploration has always worked. Each generation of technology does not just answer questions. It creates the tools that make the next generation of questions askable. The Mariner 4 engineers could not have imagined a helicopter on Mars. The Viking biologists could not have imagined a rover drilling into an ancient lake bed and sealing the core for return to Earth. And the engineers building today's sample return mission architecture are building toward discoveries they themselves will not be able to fully interpret, because the interpretive tools of the 2040s and 2050s do not yet exist. There is a version of this story in which Mars is simply a target, a destination for flags and footprints, and the geopolitical theater of a new space race. That version is not wrong about the politics, but it is deeply wrong about the science. Mars is the only other planet in the solar system where we have enough evidence of past habitability to seriously ask whether life arose independently of Earth. If it did, then life is not a rare accident. It is something the universe does wherever it gets the chance, and the implications of that ripple outward to every question about our place in the cosmos. If it did not, if Mars was habitable for millions of years and nothing living ever took hold, that silence would be equally profound. It would suggest that the step from chemistry to biology is extraordinarily difficult, that the universe is far lonelier than we imagine, and that what happened on Earth was something close to a miracle. Either answer changes everything. 6 minutes and 52 seconds of silence. That was the time between Curiosity's last command and the first data confirming it had survived. The engineers called it the 7 minutes of terror, but consider it again from the other direction. Consider that a machine humans built, guided across hundreds of millions of kilometers by nothing faster than the speed of light, landed itself in a crater on another world with sufficient precision to begin answering questions that have haunted every civilization that ever looked up at that rust-red point of light and wondered. The silence was not emptiness. It was everything we had built, doing what it was built to do, in a place we have not yet been, but are, with every sample cord and sealed and waiting, getting closer to.